It's nice to be here. I'd like to thank Tom for inviting me to talk about this topic. So I'll talk about the ranks of elliptic curves, and I will start with this short introduction to elliptic curves for those who are not number theorists. So I'll start with one ancient problem. So I'll start with Greek mathematician Diophantus from Alexandria. So he lived in the 3rd century, and he was famous for his series of books, Arithmetica, in which he usually dealt with solving some kind of algebraic equation. So one of those problems in book 4 is equation of the following form. So he did not write equation in this form. He defined it in terms of the words, but in the modern way, we would write it like this. So he wanted to find the solutions to this equation, and for him, the numbers were only rational numbers that are positive. So, I will say he sketched this curve, but he didn't really sketch this curve. He did something else. But today we would interpret his solution very elegantly in the following way. So he sketched this curve, and he noticed one rational point, minus 1, 0. And then he did the following. So he drew the tangent through that point, and this tangent intersects the curve in the 3rd point, 17/9, 26/27, which was a required solution of this problem. So today we know much more about this. So this method that was introduced here, this tangent chord process. So idea is you start from some obvious points. In this case, these are the points minus 1, 0, and 0, 0, and then you just draw all possible lines through the known points. And the remarkable fact is that in this way you will get all the rational points on this curve. So here you also have to take account of the obvious symmetry of this curve with respect to the line y is equal to 3. So this now motivates the definition of elliptic curve. So this general equation. And we will also require that certain polynomial in these coefficients, which we call discriminant, is non-zero. So this discriminant being non-zero guarantees that this curve is going to be non-singular. So what is important? So we'll look at the set of the rational points, the set of the rational solutions of this equation. And you can make this set of points into the abelian group by just following this idea over here. So you take any 2 points, you take the line to those 2 points, it will intersect the curve in the 3rd point, and that 3rd point is minus the sum of these 2 points. So it's obvious that this operation is abelian. It's not so obvious that it is associative. And the fact that was mentioned in the previous slide is that, okay, so one more thing. So we will denote by n the conductor of the elliptic curve. So precise definition is not so important. You can think of it as some number which tells us something about the complexity of the elliptic curve. So the larger conductor, the more complex the elliptic curve is. What really this conductor is, it's a number that gives information about the primes of bed reduction of elliptic curve. But this is not so important to right now. And there's this famous theorem of Mordell, which says that this group is a finitely generated abelian group. So what it means is that it's isomorphic to the product of some finite group and some R copies of Z. And that R is called the rank of elliptic curve. So for example, if rank is equal to 0, then this curve has only finitely many points. If rank is greater than 0, then the curve has infinitely many points. So now we can say that in this previous example, the rank of Diophantous curve is 2 because we have those two generators which generate 2 copies of Z. In that case, we don't have points of finite order over Q. Okay, so the main topic of this talk is computing this rank of the curve, or essentially we're asking really finding rational solutions to that equation. So it's a very interesting thing, this rank. So if you remember Mordell's theorem, we have to understand the rational points, we need to understand the torsion, and we need to understand rank. So torsion is well known, and it's know how to compute it, and it's kind of easy. But for the rank, rank is much more mysterious quantity. So, for example, it's not known is the rank unbounded. For a long time, people believe that it is. Now, there's some work that suggests that might be only finding many elliptic curves with the rank greater than 21. So the current record is 28. It was found by LMFDB. One of the possible usages of elliptic curves of high rank, which is also kind of the topic of this paper, is an observation by Montgomery from 1987. He observed that these curves can speed up elliptic curve factorization method. Okay, so just for you to get impression of how these curves of higher rank look. So this is the record curve of rank 28. So it's not kind of hard to believe that it's a difficult problem to find such an example. And these are 28 generators. Okay, so as I said, yes. What? I'm not sure.
2006. That's the same 4 numbers of the first one. Oh, okay. That doesn't coincide.
Okay, so the main point with this rank computation is that it's a difficult problem. And it's a difficult problem because it's just hard to find the rational points with the curves. So we have this descent algorithms which basically find the upper bound for this set in terms of something that's called the Selmer groups. But eventually you need to do some point search on some auxiliary curves, and you can do it just in some kind of naive way. So there's no known algorithm that will compute rank in all cases, and the curve is very complex. If the coefficients are really big, or if the conductor is really big, then it's really something that's very slow even to find any point there. So the question is very natural. Is it possible to determine rank without finding the explicit generators? So if not, maybe maybe this algorithm should not be perfect, but at least some heuristics that will tell us which curves are of the high rank and which are not. So if we would have some kind of fast heuristics, then we could just see out those curves that are probably of the high rank, and then just apply this expensive descent method on those curves. Okay, and now I'll talk about the Birch and Swinnerton-Dyer conjecture. So for every p, we define these numbers AP. These are going to be very important for us. So we subtract the number of points on elliptic curve modulo p from the number p plus 1. So if you're not familiar with the finite fields, so what we're really doing is we're using the coefficients of the equation modulo p and then trying to just count the number of solutions modulo p. So this kind of high school mathematics. So for each p, you define this number, and then you can define the following Hasse-Weil L function associated with the curve. So if S is real part of S is greater than 3/2, then this product will be absolute convergent. And the famous theorem, modularity theorem, tells us that this product with some function can be extended to a holomorphic function on the whole C. Why am I telling you this? So there's a conjecture which tells you that the order of vanishing of L function at point s equal 1, and this order of vanishing is called analytic 1, is equal to the rank of the curve. So this kind of statement is kind of a miracle if you see this for the first time, because if you look at the way how this function is defined, you're just using this AP, so you're just using the information about the solution mod P of the elliptic curve, and somehow by computing this function, you're able to see the order of vanishing at s equal to 1, this global quantity, the rank of elliptic curve. So almost nothing or not much is known about this conjecture. So it is known that if analytic rank is 0 or 1, then the algebraic rank is also equal to 0 and 1. Okay, so the idea is to use this conjecture to have some kind of heuristics that will tell us something about the rank of elliptic curve, and we'll call this kind of heuristics Mestre-Nagao sums. So the main goal here is to use these sums to identify probable candidates for the elliptic curve of high rank, and then use that more deterministic algorithm to really find the generators. So this is an example of one of this sum. So it takes this parameter P, which is the bound for the primes that we're looking for, and we'll look at the following sum. So the reason why we're looking at this sum in particular is that if you look at this exponential of this function over here, you'll really get the partial product of that L function evaluated at s equals to 1. So if you, and this, you can expect that this product should be large if it has large rank. So this is kind of the idea. To try to learn something about the rank by looking at these partial products or this sum of logarithms. Obviously, the bigger the B, the better approximation we will have. So, okay, and just mention that this sum was used by Elkies and Clarksburn as a first step in finding rank records curves with fixed torsion, cyclic torsion Z over NZ for n is equal to 2, 3 till 7. Okay, now I'll talk about our work. So in our work, we investigate deep learning algorithm for rank classification based on convolutional neural networks. So idea is to input to the algorithm conductor of elliptic curve and the sequence of normalized APs. So normalized AP, we just divide each AP with the square root of P. There's a famous theorem that says that this number AP over square root of P is always between -2 and 2. And what we do, we fix some range for primes. So in our work, we look at 3 ranges when P is equal to less than 1,000, 10,000, and 100,000. So this is the input, and the output is the rank of elliptic curve. So idea is kind of reasonable. So maybe we can do maybe in this way we can do something better than the Mestre-Nagao sums are doing. Also, I want to mention that this paper was inspired by the work of Lee and Oliver. So in their work, they were trying to classify elliptic curves of rank 0 and 1 by using some other machine learning methods. Okay, so we want to compare our algorithm with the results that are given by Mestre-Nagao sums. So for that, we were considering 7 Mestre-Nagao sums and another network omega, which took as an input all these 7 numbers. So one problem when you're trying to decide on the rank of elliptic curve based on the Mestre-Nagao sum is that it's also not clear how to do it, because you have some boundary, you compute that sum, which is the sum of some function of AP, and then you get some number, and then based on that number you should be able to say which rank that curve is. And the thing is that the number also depends on the conductor of elliptic curve. So I'll talk about this more later, but the larger conductor, the more coefficients you need for a decent approximation. So what we did, we trained a simpler, fully connected neural networks for each of these Mestre-Nagao sums. So we let the network decide on this bound. So in that way, we could better compare these 2 methods, but also in this way, we got some information about how one should really choose this cutoff depending on the conductor. Okay, just for your illustration, these are 3 more Mestre-Nagao sums that people are using in literature and that we consider. There are some other which are kind of more complicated. And as I'm
you don't fix it and then generate the data, or
yes, so we fix 3 values for B, so 1,000, 10,000, and 100,000. So for all those fixed, I mean, I'll talk later more about the training process, but yeah, so we fixed B. So we fixed B because in that way we fix the number of inputs to the neural networks, and then we can train the neural network. But as you choose larger B, you have a better classification, quality classification. And as I was saying for omega, so omega is neural network which takes as an input conductor elliptic curves and also all those other 7 sums. And what was interesting is that this neural network was usually much better than each of those sums individually. Okay, so now I'll talk a little bit about the training process, which is so in the training process, of course, the data is essential. So we use 2 databases. First one is LMFDB. So database for us, the number of isogeny classes are most important. So it's around 3 million. So we pick each curve, 1 curve from each of these exogeny classes. The reason is that the 2 curves in the same exogeny class have the same L function and presumably the same range. So we just take 1. And also, it's important to note here that LMFDB is really the union of 3 databases. First, consisting of all curves of conductor less than 500,000, all curves whose conductor is 7 smooth, and all curves of prime conductor less than 300 millions. And these curves have rank between 0 and 5, and there's only 19 curves of rank 5. So we kind of the problem with this data set is that the conductors are small. So all our classifiers were working very well right here. So we needed a new data set that contained the elliptic curves of higher rank, but also higher conductor. And so we have some custom-made data set. The problem with this curve is that it's kind of hard to construct such a database in a good way. In a good way, I mean, I will discuss how we have constructed the data set, and you'll see at the end it's a kind of biased. So first, we constructed curves of rank 0 and 1 by just taking some random Weierstrass coefficients. We know conjecture that it tells us that 100% of the curves will have rank 0 or 1. So it's easy to generate this. So conjecture that 0% of the curves will have a rank greater than 1. And for the curves of the higher rank, we did the following. So we picked some k random points in the plane, usually points of the small height, and then we just look at the curves, the pencil of curves that go through these k points. And then from those curves, we sampled some random points again of the small height. So in this way, we got lots of curves with relatively high rank. And then we were using a peri-GP function LRank to compute the ranks of all these curves. There were some curves that could not be computed. Then we discarded these curves, and also, but there's not too many of these curves. And also we know from how this LRank works that some curves will be completely missing from this data set. For example, the curves for which the 4 part of the shy is missing. Yes.
When you say randomly generate, did you put some measure on the?
No. So our intention was not to be very scientific about this process. We just wanted to generate as many curves as possible.
What does the conjecture mean when you say
what?
The conjecture is that, like with probability 1, your curve is rank 0 or 1?
Yes, but of course, here this is not the case because we already chose k rational points, and then we look at the cubics that go through these points. So these cubics, if not singular, will be elliptic curves, and they will already have these k points on them. So in that way, we force them to have as high rank as possible. So in a way, I mean, you cannot be more precise than this, but if you have an elliptic curve which has already k rational points, then it's a good chance that these points will be, maybe not all, but that they will be independent, and that this curve will have a relatively high rank. So in this way, you can force curve to have a high rank. Okay. So there is some kind of subtle bias in this construction, because in all this process, we were choosing the points of the small height. So eventually, this data set will contain lots of elliptic curves with something that's called small regulator. And this is a problem because for the curves that are small rank and large conductor, this is something very untypical, because you can expect under some standard conjectures that this regulator will be large. So because of this construction, this data set is in the following way biased. And this bias is really important for what we are doing, because if you look at really what Mestre-Nagao sums are doing, for example, that sum S5 that I mentioned at the beginning. So you're basically investigating this term log A plus R log B. If so, this is which is called original Birch and Swinnerton-Dyer conjecture, this is original observation by Birch and Swinnerton-Dyer. So what really Mestre-Nagao sum is doing is you will recognize if this leading term is large, and it may be large if this constant A is large, and it is known that this constant will depend on the regulator. So in a certain way, this will affect the performance on this Mestre-Nagao sums. But in any case, so our main intention was to compare these two models. So it's okay for us that we have this kind of bias, because we just want to know how will CNN model work compared to this Mestre-Nagao sums. Okay, so now I'll talk a little bit about the experiments that we made. So first we varied dataset, either LMFDB or custom dataset. We varied the range of APs, so we consider these three bounds, 1,000, 10,000, and 100,000. And we also varied the test curves. We have two modes. In one mode, we uniformly selected from the dataset 20% of the curves. And in the other mode, which I would call the top conductor range, we really considered all the curves in some top conductor range, and we trained the models on the curves on the range which is below this top conductor range. So in this mode, we see how the thing that the network learned generalizes to this area where it was not trained. Okay. And we also vary the type of classification. We have two. We either classified all ranks or just the binary classification, which try to determine whether the curve is of the low or high rank. So in this talk, I'll just talk about the classification of all ranks. How much time do I have? Okay, so now a few words about the modeling of this deep neural network. So this is an area of expertise of my collaborator, Domagoj. So I will not say much about this. So the architecture is the convolutional neural network with fully connected classification layer at the end. We were using a Rayleigh activation function, and the loss functions was weighted across entropy loss. We used a gradient descent optimizer Adam and autograd in the Python library. What is important, I'll talk a little bit more about this, is that we measured the quality of classification using the Matthew's correlation coefficient or P coefficient. So in the smallest case, when B is 1,000, in this case, we considered 178 primes. The kernel size was 70, and the model had approximately 773,000 of parameters. So you can see here how these layers we are looking at. So I will not say much about this. So if you want to learn more, you can look at our paper. And a few more words about the Matthew correlation coefficient. So it's a good measure for our problem because, as I said, what we essentially want to do. We want to classify curves of high rank, but there are very few curves of high rank. So when you do this kind of classification, you want to make sure that these classes with very few elements, but which are very important to us, are not neglected. And for that, this Matthew correlation coefficient is a good measure because it will punish the neural network if it tries to neglect some class altogether. So this is an example how this formula looks if you have just binary classification, but it generalizes for more classes as well. What is important for you to know is that this number will always between -1 and 1, and the bigger the number, the better. So MCC 1 corresponds to the perfect classification. Okay, now I will talk about results. So this first slide is related to that cutoff that I was telling you about. So once again, the problem is that for given curve, conductor, you're given conductor of that curve, and you're given the value of the Mestre-Nagao sum, and thus based on the data you want to decide on the rank. So for each conductor you have certain cutoff for each of these ranks, and this is what the neural network decided that this cutoff should look like. So this is how this cutoff should change when you increase conductor of elliptic curve. It's hard to make some to put something about this because it very much depends on the database. So yes.
When I get close to the singular being singular, I mean very close to the spectrum.
Yes.
How was the performance of the neural network for those cases that are very close to the spectrum?
For what those
pairs that are chosen to be very close to the experiment, and somehow the neural network could perform good or not.
I don't understand. So you're saying those curves that are very close to
The discriminant being close to a singular pair.
to the singular curve. Okay, so yeah, we didn't do that experiment.
Not being singular, but very close. The discriminant is almost zero.
Yeah, so we didn't consider this kind of experiments. Do you expect that something interesting should be going on there? Or
Usually, I had quite the same experience, but they are very close to the discriminant of the neural network and not performance well at the other form. So I expected that maybe this case will happen.
okay, so yeah, I mean, maybe we can check that then. Thank you. Okay, so now I'll show you the few tables. So first, we're going to compare all these neural networks which were trained on the LMFDB dataset with the uniformly chosen dataset test set. So recall it means that we randomly chosen 20% of the curves in the whole database. So here we'll have much curves on the small conductor that are easier to classify. So what you can notice is that the convolutional network is working really well in all three cases. It's doing much better than any Mestre-Nagao sums individually. And as I mentioned earlier, this omega neural network, which takes into account all these Nagao sums, performs much better than each of these Nagao sums individually. Yes.
So in each of these cases, it's only a Mestre-Nagao sum without any of the AP coefficients.
Yes. So each of these network has as an input conductor and the Mestre-Nagao sum. Yeah. On this.
And CNN means AP coefficients.
Yes. So CNN has input all AP coefficients less than together with conductor. Okay, so see here that both the networks are doing really well. So this is the confusion matrix, and as you can see, there are almost no mistakes in the classification, almost perfect classification. Omega classification is also doing very well. So this is this case when P is less than 10,000. This is the harder case. So this is the top conductor range case. So here we can see how does what the network learn generates to this range of curves that we did not see. So here we see that 1,000 coefficient is not enough for a good classification, but already 10,000 is for the convolutional network. But you can also see that all the Mestre-Nagao sums are struggling in all these three modes. Here the difference is large. So more okay. So if you look at the confusion matrices here, so you can see that lots of mistakes, especially with curves of rank 0 and rank 1. So in our experience, it was harder to classify these curves of range 0 and 1. The difference between these MCCs is really huge. Okay, so another way to have a feeling what does this number mean? So this model with MCC 0.9958 misclassified only 0.20% of the curves, while the best Mestre-Nagao sum in the same mode is classified 8.1% of the curves. And as I said, in this case, when P is less than 10,000, the difference is really huge.
I couldn't get the 1% from I couldn't get the 0.25%.
I'm going to get this number here. So I just look at the data. So I just go through all the curves and count how many are misclassified, and it was 0.25.
So it might not be that very. So I started with the MCC score.
No, sorry. But yeah, no. Okay. And now I'll talk about the custom data set. So here the results not that good. So first you see that in the uniform test case, the numbers are much smaller. And the second thing, there's not that much difference between the convolutional networks and the Mestre-Nagao sums. So if you compare, yes?
Could you remind me of the kind of general difference with the custom data set?
So the main point about the custom data set is that it contains the curves of much higher conductor. And conductor is the parameter that kind of determines how much AP coefficients you need to decently approximate L function. So I'll talk with you more about this later, but you can think that you need around square root of conductor coefficients to have some good approximation. So in the custom data set, the curves have conductor up to 10 to the third, while in LMFDB they have conductor up to 10 to the 10. So the difference is huge. So in a way, if you look at it from theoretical standpoint, it's very hard to expect that with so few coefficients that you could predict this range accurately. And this kind of confirms it. And this is especially visible in top conductor range, where you can see that these numbers are much smaller, and here are some instances where this omega neural networks outperforms convolutional neural network.
So how many ranks are here? I mean,
So from 0 to 10.
0 to 10.
So from 0 to 10, and in LMFDB, the ranks are from 0 to 12. So here the classification is much more challenging. So if you take the overall classification for with P less than 10,000, then uniform range, this is a simpler case. You see that here we have 23% of the curve was misclassified, but 3% of this curve prediction means true rank for more than one. So, which is in a way, it's not that bad if you just want to detect curves that have probably high rank. In the same mode, let's say Mestre-Nagao sum S1 misclassified 26% of the curves. In top conductor range, these numbers are much smaller. So here, the CNN misclassified 61% of the curves, while for the 12% of the curve, prediction missed to rank for more than one. So this is kind of some basic conclusions about the custom data set. Now I'll talk a little bit about the quality of the classification and and the relationship between conductor and bound B. So how much time do I have now? Okay, so just to have some feeling, what would we be expecting from theory that we know about the L functions? We can consider this formula over here as a toy model for detecting curves of rank 0 or 1. Because if you do it in the BSD, if this number is different than 0, then the rank is 0. If it is 0, then the rank is greater than 0. And so if you consider this equation, you will see that here in the exponent we are dividing this number with the square root of n. Which really means, if you think of it, that if you want to approximate this value decently, then you would need to consider at least the square root of n, so at least square root of conductor coefficients. So this kind of suggests that if we want to understand the quality of this classification related to these two quantities B and N, then maybe we should just look at how the quality depends on this expression B divided with the square root of N. So for this experiment, we did not generate new data. We just used the corresponding data. So I will show you two graphs. So in this graph, we look at the CNN model for those three ranges of B, and we plotted how the quality, how and C depends on the logarithm of B over square root of N. In the ideal world, when I say ideal, I mean these convolutional networks learn the same thing in a way. We would expect these three curves to be identical, but they're not identical, but they are some kind of close to each other. So I don't know what to conclude from this. The second figure is more meaningful. So here we fixed B to 10,000, and we plot this graph for the three models: CNN, Omega, and S1. And what you can see here is that the CNN is constantly better than the other two models whenever you look at it. But it also shows something that you can expect, that the biggest difference is here, somewhere in the middle. So if you have too many conditions, then all the models are working well and they're pretty close to each other. And if you have too few conditions, then the models are not doing well at all. So they're also close to each other. But let's say if you look at this data point, when MCC is equal to 0.7, here you can see substantial difference between CNN and let's say Nagao sum S1. So what you can see from this graph is that for the same accuracy, for the same quality, 0.7, you would need around 6.5 more APs for S1 than you would need for the CNN. So okay, and one more thing. So this is really about the application to finding the curves of high rank. So what one usually does is fix on a family elliptic curve. In this case, it's K3 elliptic surface, and then so in this case, this you can think of this as elliptic curve over Q of T, and you can compute that it has model range 4 and 0 for Z coordinate. So basically, what you do, you specialize this curve for different values of t, and then you have a bunch of elliptic curves for which you know that they a priori have rank 4, and this portion 0 for g. Or better to say, they will have rank at least 4. This rank can also go down. But the idea is to look at lots of curves in this family, and then hopefully some of these curves will have higher rank. So for this particular curve, there is the family that has rank 12, and in one moment this was the record for elliptic curves with these 0 for z sorting. So we just want to check our model how they work on this family. So we sampled randomly 8 curves with conductor larger than 10 to the 29. And we discarded those curves for which we could not compute a rank. And we ran this data to convolutional to the CNN for the total data set for top range for p is less than 100,000. And this is what we get. So it was quite low. But if you look at the confusion metrics, you will see that working really well for the curves of the high range. So it has a perfect classification of curves of rank 7, and also very good detection and classification of the curves of rank 6. So it's kind of plausible that it would be useful for detecting plausible candidates for the curves of the high range. Okay, and now a few concluding remarks. So it's not clear why CNN works much better than other Mestre-Nagao sums on the LMFDB dataset. So the question is, did this neural network discover some new mathematics? So what seems to me is that in certain range of B, when B is very big, both models will do well, and then the difference will be larger and larger, and then when B is again too small, the models will not work, so they will become equally bad. But in some range, the CNN works much better. So if you remember that situation when P was less than 10,000, so CNN had 0.9 MCC, and the other Mestre-Nagao sum had 0.5. So that's an interesting question. What's going on here? And there's some other ideas of what one can do along this line. So you can provide the root number of the elliptic curve of the size of the sparage group to the neural network, and then see what you will get. Of course, the root number will significantly improve classification because it determines the parity of the rank, and for the size of the sparage group, it's not so clear. So one would need to try this. So another idea is to play with these neural networks which are modeling Mestre-Nagao sums. So here we're just taking one number as an input together with the conductor. So the sum of first B coefficients, but maybe the classification would be better if we provide more partial sums. Especially if you remember that remark about the original DLD conjecture. If you have two partial sums, if you subtract them, then you will get something that will not have that constant A in the formula. So it might be useful to try this to see how the Mestre-Nagao sums will work in this case. And also one can try to construct new improved Mestre-Nagao sums. By choosing some coefficient which will weight each of those parameters. So this is something one can try. Okay, thank you very much for your attention.